Today, we're diving into a cosmic detective story. Seriously, it's a puzzle that puts two of our most fundamental theories of the universe head to head. And what's at stake? Oh, just the very nature of reality and a core principle of physics we all thought was completely unbreakable.
It all kicks off with this really huge question. What is the world actually made of? We're used to thinking about matter and energy, right? But what if there's something even more fundamental? What if the entire universe is actually made of information?
This idea, which was championed by the legendary physicist John A. Wheeler, well, it pretty much reframes everything. It suggests that the instructions to build a thing are just as real, maybe even more real, than the thing itself. And if that's true, then what happens to that information becomes one of the most important questions in all of physics.
Now, when a physicist says information, they mean something super specific. It's all the unique quantum data that describes a system, like every particle's position, its velocity, its spin, the whole shebang. And a core law of the universe is that this information is conserved. It can get scrambled, rearranged, or hidden, but it can never, ever be truly erased.
Okay, so let's get into this. Because if information can never be destroyed, we've got a huge problem. We've found a place in the universe that looks an awful lot like a perfect crime scene. A place where information checks in, but it never ever checks out.
Think about it like this. If you burn a book, yeah, you've destroyed the cover and the pages, but you haven't destroyed the information itself. It's just been transformed into heat and smoke and ash, and if you were incredibly patient and smart, you could theoretically reverse that whole process and reconstruct the book. The information is still there. But when a black hole swallows that same book, something totally different seems to happen. That information crosses the event horizon, and for all intents and purposes, it's just gone. Forever. And this brings us to our prime suspect, and the brilliant mind who put it on the wanted list. Back in the 1970s, Stephen Hawking made this incredible discovery that turned black holes from just cosmic vacuum cleaners into these deep philosophical paradoxes. So Hawking realized that when you mix quantum mechanics with gravity right at the edge of a black hole, something really strange happens. Turns out, black holes aren't these eternal prisons after all. They actually glow, just super faintly, with a kind of thermal energy that we now call Hawking radiation. And what that means is over these truly mind-boggling timescales, they evaporate away to nothing. So how on earth does this work? Well, all around us, even in what we think of as empty space, pairs of virtual particles are constantly popping into and out of existence. But right at the edge of a black hole, sometimes one of these particles gets sucked in while its entangled partner manages to escape. And to someone watching from far away, it looks like the black hole just spat out a particle. That escaping particle is Hawking radiation, and it slowly, piece by piece, carries away the black hole's mass.
Okay, let's really dig into this graph, because this is the heart of the whole crime. You see that blue line? That's the black hole's information content. It's entropy, and it's steadily going down as it evaporates. That makes total sense. But look at the red line. That's what Hawking calculated for the radiation. It's just random thermal noise, and its entropy just keeps going up and up and up. And then poof, the black hole is gone, leaving behind nothing but this high entropy radiation. The original information vanished. And that is a massive violation of everything we know about quantum mechanics.
For decades, physicists were just totally stumped. I mean, how could this be? The solution, or at least the first major clue, came from a completely different and frankly mind-bending direction. It came from the idea that our universe might not be what we think it is.
Okay, stick with me here because this is where things get really weird. It's called the holographic principle. It was first proposed by Gerard 't Hooft and then developed by Leonard Susskind, and it suggests that everything we see and experience in 3 dimensions might just be an illusion, a projection of information that's stored on a distant 2-dimensional surface.
It's a wild thought, right? The idea is that all the information needed to describe you, me, this planet, the entire galaxy, it could all be fully encoded on some kind of boundary surface, like a cosmic hard drive. And the 3D world we're all living in would just be a holographic projection of that 2D information.
And this is where the idea gets, really powerful for the people actually doing the math. This principle basically says that a really difficult theory that includes gravity can be perfectly equivalent to a much simpler theory without gravity that lives on its boundary in one fewer dimension. It's like they're 2 different languages describing the exact same reality.
So how does this totally bizarre holographic idea help us solve our crime? Well, it turns out it gives physicists a brand new tool to calculate the information coming out of a black hole. And the results? They were absolutely revolutionary. So this brings us to the crucial question.
If information really is preserved, like quantum mechanics demands it must be, then it has to get out somehow. The Hawking radiation can't just be random thermal noise. It has to be carrying the information of everything that fell in. But how?
Now check this out. See that green line on the graph? That is the aha moment. A physicist named Don Page figured that if quantum mechanics is right, the radiation's entropy couldn't possibly follow Hawking's red line. No, it had to follow this green one, which we now call the Page curve. It rises for the first half of the black hole's life, and then, and this is the key, it starts to fall, perfectly mirroring the black hole's own decreasing entropy. When the black hole is gone, the entropy is back to zero. Information is saved.
And that turning point on the graph? It's so important it has its own name, the Page time. It's basically the halfway point in the black hole's evaporation. Before Page time, the radiation coming out is entangled with the stuff that fell in. But after Page time, something amazing happens. The new radiation starts becoming entangled with the radiation that already escaped. It's creating this web of connections outside the black hole. And that is how the information starts to leak back out into the universe.
But, just knowing the right answer isn't enough. For years, the Page curve was just a prediction. Physicists knew what the graph should look like, but they had absolutely no idea what physical mechanism could possibly make it happen. And the final reveal, well, it's even stranger than the hologram.
To figure out the how, physicists used that holographic principle as a new kind of mathematical tool. And their calculations pointed to this incredible new idea involving something called islands, these bizarre little regions of space-time that completely change the game.
Okay, so here's how this insane rescue mission works. Late in the black hole's life, after that Page time we talked about, a region deep inside the black hole, this island, suddenly becomes quantumly entangled with the radiation way, way outside. It's almost like a tiny wormhole opens up, connecting the heart of the black hole to the escaping radiation. And that means the information inside that island is now, from a quantum point of view, part of the outside. It's a backdoor that lets the information be accounted for even as the black hole itself is vanishing.
And this diagram, I know it looks complicated, but it illustrates the idea brilliantly. It shows how that internal region, the island, can be thought of as part of the exterior. The information isn't in two places at once, but our description of where the outside of the black hole even begins, that changes. It's this subtle but incredibly profound shift that finally allows the Page curve to bend back down and save information from oblivion.
And just like that, the case is pretty much solved. The fundamental law of physics holds. Black holes aren't cosmic shredders that delete the universe's data. They're the ultimate scramblers, the most complex hard drives you can possibly imagine, but at the end of the day, they give back everything they take.
Which, brings us right back to where we started. Solving this paradox just reinforces that powerful vision of information being a fundamental building block of our world. It seems the universe works tirelessly to preserve it, even if it has to invent bizarre quantum islands and holographic projections just to pull it off.
So the next time you look up at the night sky, remember that the story of the stars, the planets, and even you is written in information that the universe will absolutely not allow to be lost. Which leaves us with one last, really unsettling question. If the 3D reality we all experience is just a projection from a distant 2D surface, what does it even mean to be real?